Hi, everyone. So Professor Monty here. We're going to learn today the derivatives of a to the x and log base a of x. Now, there's two simple ways to show the derivatives here, which I'm going to show you. So I'm going to show you how to take these derivatives first, and then I'm going to spend most of the time just doing examples. I will show a proof of the first derivative just so we see it, but recall from what we did before. I'm changing the pen because I don't want that color pen. So let's do this. All right. So recall from what we did before, we saw that the derivative of ln of x was just 1 over x. And the derivative, well, that's a weird looking and. Let's clean that up a little bit. And the derivative of e to the x was just e to the x. And of course, I'm going to say, remember the chain rule. Because we do have to remember that. All right. Exclamation point. Make that important. Now, what's happening here, though, is we're going to look at bases other than e. And so the first one, and again, I'm just going to show you the rule. We'll just even say rule. If I take the derivative of some other base, let's call it a to the x power. So base at all. The derivative of that is actually going to be, you get back the entire exponential just like we always have been. We get back a to the x, but then it's times the ln of a, whatever the base was. And it looks a little bit weird. Notice this rule still works with e to the x. We'll put that over here as a note. If I had done the derivative of e to the x and I followed this same rule, I'd get back the e to the x, but then times the ln of e. Well, the ln of e, that's ln of e to the first. ln and e cancel each other out. This just becomes e to the x times 1, which is just e to the x, which is what we know the derivative of e to the x is. Let me just flip. Oh, yep, there it is. So we saw that from before. So this isn't changing anything. It's just saying if you have a different base, you have to say times ln of whatever that base is. If it's e, you don't have to say it because ln of e is just 1. All right, that's our first basic rule. We need to remember that. I'm just going to put a big box around it to help us remember that. That's one of the two rules we're going to see today. I'll show you a quick proof of it. And you don't have to know the proof. I just, as a math teacher, kind of feel obligated that I should probably show you this proof. And it's a very simple proof. Hopefully you can follow along. If not, no big deal. But we're taking the derivative of a to the x. We're trying to figure out what that is. Well, one of the definitions of logarithms is I can call this the derivative of e raised to the power of ln a to the x. Now, two reasons I'm doing this. One, I'd like to have that ln in front of the a to the x, because remember, if that's an exponential, the way I get an exponent down that's a variable is to take the ln, some logarithm of it that'll allow me to take it down. But I can't just randomly take the ln. I don't have an equation here. I can't take the ln of both sides. But if I do e to the ln of a to the x, I can do that because that's one of our properties of logarithms. Just like when we had ln of e, those cancel out, e to the ln cancel each other out, you just get the argument. So that is just mathematical. Hopefully you remember that from college algebra. Again, you might not. We don't use it a whole bunch. Okay, so now I've got that. Now I can bring that x down in front of the ln. That's why I did that. So I'm still taking the derivative, but now what I've got is e to the a times the ln of x. Oops. I wrote that completely wrong. Bear with me for a second. I looked at what I had above that and I said, that's not true. I'm bringing the x down times the ln of a. Hopefully some of you caught that and you thought, why in the world did he do that? Okay, so now I have x times the ln of a, which becomes the derivative of, notice I haven't taken the derivative yet, I'm just doing some algebraic manipulations. It's the derivative of e to the ln of a times x. That's just the commutative property of multiplication. I'm just switching the order that I'm multiplying those together. And the reason I'm doing that is because I want to take the derivative of that. Notice that's that ln of a. In this case, it's a constant. A is not a variable. It's a constant. It's whatever the base is. The variable is x. So that's similar to think if I'm taking the derivative of, it's not a very good derivative. If I'm taking the derivative of, say, e to the 5x, we all know how to take that. It's e to the 5x, but then the chain rule says times 5, because the chain rule. That's what I'm going to do here. I'm using that ln of a where the 5 is, because it's a constant. I don't know it's a 5. I don't think it's a 5. It's probably an irrational number since ln of something. But I'm using that same rule because now I can actually take the derivative. So the derivative, remember, I get back the entire e to the power. But then the chain rule says times the derivative of that exponent. Well, the derivative of the exponent is the ln of a. So this piece right here was the chain rule. Okay, that's the 5 from that other example I had done. So now I've actually taken the derivative. Now I'm just going to clean it up a little bit. So I can write this let's say this so that it looks a little bit more familiar. I'm using the multiplication. I'm using the commutative property of multiplication again. So instead of ln of a times x, I'm doing x times ln of a. I've still got this ln of a on the outside. And the reason I'm doing that now, property of logarithms, this exponent can go back up there. And that's really e to the ln of a to the x times the ln of a. And then another property of exponents, the e to the ln cancel each other out. Those are inverses. I just get a to the x times the ln of a, which is what we said the derivative was. So remember, that's going back up here. That's the derivative of a to the x. So the derivative of a to the x, you get back the a to the x, but times the ln of a. Again, that's the proof. If you followed it, fantastic. If you didn't follow it, that's perfectly okay. What I want you to get out of here is that, well, we can just look at it right here, that the derivative of a to the x, where a is any base, remember the base has to be a positive number, can't be equal to 1, but for any number that a that satisfies those requirements, the derivative of a to the x is always the same a to the x you start with times the ln of a. Okay, so that's the derivative of a to the x. I'll show you the derivative of ln of x, so we have those together, although I'm not going to go through the proof. The proof is in the book if you want to see it. We'll just say also, so similarly, if I take the derivative of oops, I don't want ln of x, I want some different base. So take the derivative of log base a of x. What are we going to get there? Well, similar to when we had the derivative of ln, where it's just 1 over x, we still get back that same 1 over x. But we have a different base, so it's going to be times, just like what we did to a to the x times ln of a, except since the x went to the bottom, so does the ln of a. So it's just 1 over x, just like it was with ln of x, but then times 1 over ln of a. Again, had that been log base e, or ln, it would be 1 over ln of e, which is just 1 over 1, again, which would just simplify the whole thing to 1 over x. So that's the other one. I'll put both of these here boxed. These are the two you need to know. So the first one, the derivative of a to the x. The second one, the derivative of log base a of x. And so from there, we're just going to do a bunch of examples, a couple word problems, and that'll take us to the end of this section. All right, so bear those in mind, and we'll see a lot of examples, so hopefully those will be readily accessible in your brain. But here's the first problem I want to do. It's just problem 2. It says y equals 7 to the x. And all these problems just say differentiate. They're just going to give us some practice finding derivatives until we get to the applications. Okay, so y equals 7 to the x. They want us to take the derivative. Again, they're usually going to call it dy dx. If you want to call it y prime, you're welcome to do it. But think, what do we get? We get back the entire exponential times the ln of whatever the base was. That's it, done. So just remember times ln of the base. Do another one quickly so that you see it really is that simple. F of x is 15 to the x. And so think about what that derivative is going to be. If I take f prime of x, I get back 15 to the x. Always, always, always get back the exponential, but then times ln of the 15. And ln of 15 is an irrational number, so we could find a calculator approximation, but we don't want to round it off. If I leave it as ln of 15, I haven't rounded anything off. That's the exact answer. Okay, let's go another step. We're just cruising through these examples. Here's problem 6. They say lowercase g of x is equal to x to the third, and then in parentheses, 5.4 raised to the x power. Now, what they've done is they've combined two things. They've combined this x to the third, which we call a power function, because the power is a number, times the 5.4 to the x. It's called an exponential because this time the x, the variable, is up in the exponent. But notice these are multiplied together. So when I go to take the derivative, I'm going to have to use the product rule. All right, so remember the idea is if this is considered f and this is considered g, then the product rule is the first f times the derivative of g plus g times the derivative of f. So when I do that, I get g prime, and this first g of x not to be considered with the g that I'm doing for the g prime and the g, but you're probably used to that from what we do in class. So we've got the first, x to the third, times the derivative of the second. Remember, we get back 5.4 raised to the x, but then times the ln of 5.4. So that's the first. This is the first times the derivative of the second. This is the chain rule. It is the chain rule. We usually don't. That's not really the chain rule. Let's erase that. Let's not misspeak there. So the first times the derivative is just part of the derivative. The first times the derivative of the second plus the second 5.4 to the x times the derivative of the first. Oh, power function, just our regular way of taking a derivative. So this was g times f prime. Put a plus in there so we have the full product rule. So there's my product rule. They're going to go another step and out. So they're not going to leave the answer there. So here's what they're going to do. Notice, and I've only got two different pieces here, two different terms. I've got this first term and I've got this second term. Let's factor out what they both have in common. First of all, I'm going to factor out, if I look at the x to the power, I can factor out an x to the second because they both have at least two of them in there. I can't factor out the x to the third, obviously, because the second one doesn't have an x to the third. But I can factor out an x to the second. It's still going to leave me with one x from that first piece. Also, they have in common the 5.4 raised to the x power. Now, I've factored all that out. I'm going to put a bracket here so we don't get it confused with the parentheses. So what's left in the first piece, I still have one of the x's left, and I still have the ln of 5.4. In the second piece, I took out that 5.4 to the x, I took out the x squared, but I still have the 3. And you can use a parentheses there instead of a bracket, but that's fully factored, because now if I wanted to find relative extrema, set that equal to 0, x squared equals 0 at 0, 5.4 to the x, again, the exponentials by themselves never equal 0, so that's not going to give you a critical value. But the x times 5. ln of 5.4 plus 3, that I could set equal to 0, subtract the 3, divide by ln of 5.4, and I'll get a second critical value there as well. But here's my derivative fully factored. All right, so we have to worry about the product rules, all that kind of stuff, quotient rules as they come up. Here's problem 14. Now they're going into a logarithm, still just asking us to differentiate it. Log base 4 of x. Y equals log base 4 of x. And so remember the rule, just like ln, we start when we take the derivative, we get 1 over x. But it wasn't ln, so I have to say, oh, times 1 over the ln of 4. And a lot of times they'll put that as one piece. I like it separate, but they mean the same thing. I like it separate because it highlights, oh, it's 1 over x, just like it was with ln. But then we have times this other piece. So do realize you may see it in either format. And I know I'm going pretty quickly through this, but luckily you'll be able to rewind the tape and listen to it as many times as you want to, if you want to. So g of x, log base 6 of 5x plus 1, all in parentheses. Now remember what happens, I get 1 over the stuff that's in parentheses, whatever I'm taking the log of. So g prime of x, 1 over 5x plus 1. The chain rule says times 5 because I had an inside function. And then since it was log base 6, I have to say times 1 over ln of 6. And this, they would probably at least put the 5 on top of the first fraction, if not write it as a single fraction. So they'd probably either write it as 5 over 5x plus 1 times 1 over ln of 6. And if you wanted to factor out, or multiply those together rather, they'd go numerator 5, bottom, I don't know which one they'd put first. We'll just leave it in the order it is. I like the top one better, but when you're looking at the answers in the back of the book, it may be the bottom one. They may consider that more simplified since we actually did that operation of multiplying the fractions together. Just realize you cannot cancel those 5s because that plus 1 on the bottom. All right, so let's move on from there. We've got, I just have 2 more problems picked out before we jump into a couple applications. So let's see, this is 26. And again, what you may want to do after I write the problem down, you may want to pause the recording, try to take the derivative yourself, and then see what I do, see if we get the same answer. And in fact, that's a very good way to practice, is as you're going through these, maybe the second time, or maybe when you're going through to practice for the exam, you pull up one of these lessons, and as you watch it, each problem that I do, you say, okay, let's see if I can do this one. Okay, let's see if I can do this one. And just pause it, work it out on a piece of paper, and then see what I do. And hopefully you'll get better and better, and you'll be able to get all the right answers. Okay, so again, we'll call this dy dx when we take the derivative. Again, it's a product rule problem because you have that 6 to the x times log base 7 of x, and there's an x in both of those pieces. So if I go the first, 6 to the x, times the derivative of the second, 1 over x times 1 over ln of 7, plus the second, log base 7 of x, times the derivative of the first, 6 to the x times the ln of 6. So there was some good practice for us. So there's the first times the derivative of the second, plus the second times the derivative of the first. There's my product rule. Now, we can factor out that 6 to the x. That's the only thing common to factor out, and then I'll clean it up. Yeah, there's not much to clean up, I guess. dy dx. But I am going to factor out the 6 to the x because they both have a 6 to the x. And it's going to leave me with 1 over, we'll just call it x ln 7 plus, and then in the second piece, I'm sorry, that dot keeps making me think that's an I. I'm going to erase that dot right there. We'll just move it up a little bit higher. That was for the multiplication of the f times g prime. So 1 over x times ln of 7 plus, I factored out that 6 to the x. So let me show you what I factored out. I factored that out and that out. That's why those are on the outside. Those are here now. And then 1 over x ln 7 over here. I'm just going to leave it the way I see it. I'm going to go log base 7 of x times ln of 6. And we may want to put a parentheses around that log base 7 of x just so we don't think that it's log of that whole thing. And then that'll be my answer. I'm going to erase this circle here since you've already seen it. And I don't want it in my answer. So there's my derivative. And this, I'm going to clean this 7 up a little bit. I like to, make it a little bit more so that when you're looking at it, you can easily see what they are. All right, so that's my derivative. Again, it was the product rule, and then I just factored some stuff out. And you may feel lucky. I'm looking at these problems. There's no quotient rule problems, so I'm not going to do a quotient rule problem with you, but I will do one more product rule problem before we go into the couple applications I've picked out. So they give us capital F of x, and it's log base 9 of x times, and then in parentheses 4 to the x. Oops, I'm doing the wrong problem. Let me erase that. Sorry about that. The capital F of x is right, but I moved to the wrong problem. It's 7 to the x times log base 4 of x raised to the 9th power. So I wanted to do this one because it shows that it throws that exponent in there, which changes things a little bit. We're going to have to use the power rule just as if that was x to the 9th power when we do the derivative of that piece. But again, product rule. I'll write that up here again. Product rule. So it's the first times the derivative of the second. So it's going to be bring down the 9 times all this stuff to the 8th power. But then the chain rule says times the derivative of the inside, which is 1 over x times 1 over ln of 4. That's the biggest chain rule we've ever done. So that was the first. All of this is times the derivative of the second, plus the second log base 4 of x to the 9th times the derivative of the first. 7 to the x times ln of 7. So the second times the derivative of that's it. It's kind of a mess. We'll factor out some stuff. We'll clean it up a little bit. So there's my derivative. And notice some stuff we can pull out. They both have a 7 to the x. So we'll pull that out. And when I look here, they both have at least 8 of those. When I pull 8 out here, I'm still going to have 1 of these left. That's supposed to be a 1. I still have, let's do that in blue. I'm still going to have, I don't know where to put it. I'm still going to have 1 of these left. So let's factor it out. Capital F prime of x equals, pull out the 7 to the x. Those are gone from both. Also pull out log base 4 of x to the 8th power. And then let's see what we have left. Again, I'll put brackets. You can put parentheses if you don't like the brackets. but I've got both of the blue circles in the first one. I've got the 9 left, and then I've got that other stuff from the chain rule. So I'm going to have 9 on the top. The bottom is going to be x ln of 4. And you know what? It's bothering me running into that other stuff. I'm erasing all this. We're gonna just start this piece over because I don't want you to look at it and get confused with some of that other stuff. So let's move that down quite a bit. F prime of x. So we factored out the 7 to the x. Wow, that was crazy. We factored out the 7 to the x. We factored out log base 4 of x, 8 of those. And so it leaves me with 9 over x ln 4. That's my first parenthesis, or my first piece. That was from all of this. And then when I look at that second piece, let's see what's left. So the 7 to the x is gone. That log base 4 of x to the 9th, I still have one of those left. So I'm going to move the ln of 7 in the front and then say times log base 4 of x. Now notice it's to the first power. We typically don't put the first power, so I'm just going to erase that. But that's what we have left. It looks like a big, long, ugly problem, and it sort of is. I definitely wouldn't want to take that stuff that's in the bracket and set it equal to 0 and try to solve, but that's what computers are for, I guess. Okay, so a lot going on there. I just wanted you to see, one, that crazy chain rule was a little bit messed up, but just go just a step at a time. And there's a lot of stuff in there. You might get confused, but again, at least you can rewind and go step by step a little bit slower if you need to. All right, so let's jump in. I've picked out 2 application problems to do. The first one is problem 38. It's called recycling aluminum cans. And it says this. It said, it is known that 45% of all aluminum cans distributed are recycled each year. Here, let's even write that down. 45% of aluminum cans recycled each year. All right. It says a beverage company uses 250,000 pounds of aluminum cans. So they use 250,000 pounds. They use the LBS abbreviation of aluminum cans. After recycling, the amount of aluminum in pounds still in use after T years. So after T years, number of pounds, and they write, well, I'm not going to write, we don't need to know that. Number of pounds still in use, N is, so they give us a formula, N of T, so the number of pounds after T years, 250,000 pounds times 0.45 raised to the T power. And so that's why I wrote down as much as I wanted to, because notice this is very similar to what we were doing before, where we had the initial value times e to the kt. Well, this time we don't need an e to the kt, because if 45% of the cans are recycled, that's what this 45% right here is. That comes from. So they're saying, look, after 1 year, I'm going to multiply that 250,000 pounds by 45%. That's how much there still is, because those have all been recycled. And then I would multiply that again by 0.45 in the second year. Well, that's that T, once that's a 2, that means you have 0.45 twice. And so this is a very easy way to build a function if you know how it's changing each time. Now, the bad part about this as opposed to using E is that it's going to be a slightly worse derivative because I have to attach that times ln of 0.45. So, which is, again, irrational. So it makes the derivative a little bit worse, but it was very easy to build the function. Okay, and they had already built the function for us. We didn't have to do it, but their first question says, find n prime of t. So part A, find n prime of t. Well, that's going to be easy. I'm going to clean up that n because I just wanted to look a little bit nicer. So what do we get? The 250,000, it's a constant multiple, so it stays. The exponential always stays. Now, there's no chain rule here because that t power is just t power. No chain rule, but we do have to say times the ln of 0.45 because of having that different base. Now, that's the exact value of my derivative. By that ln of 0.45, which is a constant, times the 250,000, you could, but again, we'd have to round it off. And however many decimals you have to round to is going to determine what you're going to want to do. I'm just going to leave it like that. Part B says interpret the meaning of n prime of t. Now, I'm not going to just interpret that. I will say it in words. I'm not going to write it down because I'm going to change the problem a little bit. So n prime of t, remember, n is the number of pounds in use. N prime of t is the rate of change of number of pounds in use. In other words, how many pounds are we changing each year? So what's happening to the number of pounds we're going to have the next year? And again, it has to be a very vague general definition if we just do n prime of t. So what I would typically do is I would put in something like find n prime of 6. And then we can actually find a value. So we'd say, oh, that's 250,000, 0.45 raised to the 6th power times the ln of 0.45. Now I'm just going to plug that into my calculator. 250,000 times 0.045. Oops, I put the 0 in the wrong place. 0.45 to the 6th power times the ln of 0.45. And I get negative, and let's go, remember, this is in pounds per year is what this is. Negative, I'll go to the nearest pound, negative 1658. And again, that's in pounds per year. That's my rate of change. Well, this I can actually interpret to what it literally means. That comma didn't show up very well. We'll erase that. I guess didn't mean to erase the pounds. Okay, so here's literally what this means. That's in the 6th year, that's how it's changing. So our interpretation would be interpretation. And remember, we're always predicting for the next period, so the next year in this case. In year 7, we expect to lose because it's negative. We expect to lose 1,658 pounds of aluminum. From circulation. But notice just seeing a generic formula doesn't really tell us much. But when we actually work it out in our calculator, we get a negative number. It says, oh, we're losing, we're going down in pounds. which is what's happening because we lost, if we recycled 45%, 55% of the amount of aluminum cans that still existed in year 6 from that original 250,000 pounds. Whatever existed in year 6, going into year 7, we're going to lose another 1,658 pounds of those aluminum cans that ended up in the landfill or whatever they did. They did not get recycled. They've gone out of circulation. But that's why I like putting a number in here so that we can actually have a nice interpretation and see what things mean. All right, so I like that problem real well, especially after I changed the wording, but that's the way I would ask. And the next problem has a similar type of question that they ask as well. All right, so let's go from there. So that one, our formula, we had that 0.45 to the t. Now that 0.45, again, that was 45% is recycled, but that also, since that was less than 1, that's smaller and smaller numbers. Okay. So problem 40, it says the total financial liability in billions of dollars of US households can be modeled by. So L of T equals 1547, 1.083 to the T. L equals liability, in other words, how much households owe in billions of dollars. Billions, here, I'll put the dollar sign there. In billions of dollars, T years after 1980. And so this is household liability. So in households, what do you owe on your mortgage or your home loan? How much do you owe on personal loans? How much you owe on credit cards, student loans? What do you owe? And notice this time the base 1.083 is above 1 because it's going up. So if it's at 1, it doesn't change. If it's below 1, like the 0.45, it's getting smaller. If it's above 1, it's growing. And this is growing at 8.3%. That's what that 1.083 means. You get back, the 1 gives you back your original number. The 0.83 gives you an 8.3% growth rate. Okay, they graph this, but notice it's an exponential graph. So the graph has to look something like this. It's going to start someplace in 1980. Well, it starts at 1547, and it's growing exponentially. It goes up at 8.3% per year. And I might have had a little steep there, but that's fine. We just are getting a general idea of how that looks. So let's see. Part A, using the model, predict total financial liability of U.S. households in 2012. Predict household liability in 2012. Well, what that's going to do, they're predicting T for us. So 2012, remember we started in 1980, so that's 32 years. So they're just saying find L, find the liability after 32 years. So I go 1547, 1.083, raised to the 32nd power. So it grew at 8.3% for 32 years. All right, so let's see. 1547 times 1.083 raised to the 32nd power. And I get 19,842. And let me see how many decimals we want to go to. Oh, that's plenty. And here's why. Because this is in billions of dollars. So if I move the decimal 3 places, so I'm going to take this blue pen. If I start here and I go 1, 2, 3 places and I move it there, the value is really 19.842 trillion. Now, if you said 19,842 billion, you're right. That's the same thing. So this would have been 19,842 billion. Same number. But almost $20 trillion. All right. Part B says, find L prime of 25. And then they're going to ask us to interpret that. Well, the first thing we need to do is find L prime of t. So let's find the derivative. So let's see, there's my L of t up there. Keep the constant multiple. Keep the exponential. But then since that wasn't a base e times the ln of whatever that base is, 1.083. All right, so there it is. I'm just going to plug in 25 for the t. So L prime of 25, 1547 times 1.083 to the 25th power times the ln of 1.083. All right, so let me plug this into my calculator. Let's see what we get. 1547 times 1.083 raised to the 25th power times the ln 1.083. And I get 905. And let's see where the book rounds this. They just leave it there. So we'll go 905. It's not a very good 5. 905. And remember, that's in $billion per year. That was kind of crazy. So $905 billion per year. Specifically, now remember, it's rate of change. So it's, we put it as L, but it's DL dt. The change in liability over the change in time. Well, what's the change in liability? $900. What's the change in time? 1 year. So it's 905 billion per year. That's where those units came from. The interpretation for part C, remember, it's always forward looking. So it's the next year. So that was in the 25th year. In 26th year, let's see, 26th year, we started in 1980. So that'd be in 2006. We expect household liability to increase, because it's positive, by $905 billion. Now, we don't have to say per year because we're only talking about 1 year. We're talking about the 26th year. So that is per that year. So per the 1 year. So in the 26th year, in 2006, we expect household liability to increase by $905 billion. All right. So that's all the material. I gave you a bunch of examples. Hopefully that helps out. Remember the 2 big takeaways. Let's list that. 2 big takeaways. One is the derivative of a to the x is a to the x times the ln of a. And 2, the derivative of log base a of x is 1 over x, just like with ln, but then times 1 over the ln of a. Those are my two big takeaways for the day. Everything we did today is based on those two. All right, so those are the only new things. I know we talked for a long time, but that's what's new in this section. Everything else is stuff new. Product rules, power rules, applications, interpretations. Those are 2 new ideas. All right, hopefully that helped you. I think you work on this, you'll get a good idea what's going on, and best of luck to you. And remember, you can do this.